let's look at some applications of the chain rule, how to take derivatives of some composite functions. And it's usually good to start with an example that you can check in other ways, not using the chain rule. That way it will reveal some of the mistakes that a lot of students make at first when applying the chain rule. So that's why I said here, find dy dx in two ways. The first way is not even to use the chain rule, but look at the expanded version of y, which is 4x to the 8th plus 12x to the 4th plus 9. And if we want to find dy dx, we'll just use the power rule. So that's going to be 32x to the 7th. I don't like how that 7 is floating up there. 32x to the 7th plus 48x to the 3rd, and the derivative of 9 is 0. So we're done. Let's now use the chain rule to view the unexpanded version as 2x to the 4th plus 3 squared, in other words, as a function composition. And you might be asking, well, why would you do that? Because why can't you just expand it out? The reason we're going to do this is because what if that 2 over there, that exponent 2, was 100? You don't want to be multiplying out 100 binomials just so you can take the derivative. The chain rule is going to get at the answer without us having to expand it. So before we do this, let me just point out what the biggest mistake that students make is. They would say, okay, y equals 2x to the 4th plus 3 squared. And then they'd say dy dx, well, you just bring the 2 down, that outside 2x to the 4th plus 3, and then you just diminish the power by 1, and you're done. Now the reason this isn't right is, first of all, we only did half the chain rule. We took the derivative of the outside part, but didn't times by the derivative of the inside part. The reason I start with this simple example is just compare this to what we have on the left. If we distribute that 2, then we do not get what we know we should be getting, which is 32x to the 7th plus 48x cubed. So this is not true. All right, we're missing a part of that problem. I'm going to start by using an intermediate dependent variable. So I'm going to say, well, y equals 2x to the 4th plus 3 squared. I'm going to pretend that that's really just, y is something to the squared generally. So y equals u squared. And clearly I was letting my u be 2x to the 4th plus 3. Now let's take these derivatives. So dy du is just equal to 2u, and du dx is equal to 8x cubed. Now according to the chain rule, if I want to find dy dx, which is what I want to find here, dy dx is going to be dy du times du dx. And now we just substitute. Dy du is 2u, and du dx is 8x cubed. And so we are almost done. It's just that dy dx should really just be a function strictly in terms of x. So since I know that u is what I'm calling 2x to the 4th plus 3, I can just substitute that back in to get my final answer, 2 times 2x to the 4th plus 3. And notice that's where we stopped up here above in the wrong example, right? What we forgot to do was times by the derivative of this next of du dx, which happens to be the inside, and that's 8x cubed. And if you distribute that, distribute the 2 and the 8, you'll see that you end up getting 32x to the 7th plus 48x cubed, which is what we wanted to have happen. And by the way, you don't need to expand that out. Especially in calculus, you can often get away with not expanding, but I just wanted to do it to prove that it ends up being the same as what we have over here. Alright, so there's an example of the chain rule. And again, you'll see that this is very useful if this problem was 2x to the 4th plus 3 raised to the 200th power. The chain rule is going to let us take that derivative really quickly rather than just having to expand that all out. In addition to the Leibniz notation of the chain rule, once you get good at it, you may find you don't need to write that out so much, and you can start viewing composition functions at a glance in terms of an inside and an outside function. So, as an example, let's say f of x equals 2x cubed minus x, and we want to find f prime of x. We could use the Leibniz notation. We could say, let's call f of x y instead. We could say y equals, I could say y equals sine of 2x cubed minus x, and I'll re-express this problem. Instead of find f prime of x, I could just say find dy dx, just using different notation. And then I could just use the chain rule by introducing an intermediate variable, like u, and I could say, well, y is really just the sine of something. It's the sine of u. And u is what I'm calling 2x cubed minus x. And according to the chain rule, I know that dy dx is equal to dy du times du dx. And I just need to find those derivatives. So dy du, the derivative of sine is just cosine, and du dx is just 6x squared minus 1. And we make those substitutions. Dy du is cosine of u times du dx, which is 6x squared minus 1. And cosine of u, since we want to write this in terms of x, u is 2x cubed minus x, so it's the cosine of 2x cubed minus x times 6x squared minus 1. And there's the chain rule. So we've already done an example like that. What I want to propose to you is that you can, as you get good at this, you may not need to use this fraction form of the notation. In other words, you could just say, okay, well, f of x equals 2x cubed minus x. So therefore, f prime of x is equal to, well, the derivative of sine, which is cosine of something. Now, what is that something? Well, it's the derivative of sine at its input. And what's being inputted into sine? 2x cubed minus x. This harkens back to that very first video on the chain rule that I put in, where we sort of acknowledged or recognized that the input to cosine, or the input to sine right now, is another function. So we're taking the derivative of the outer function at the interior function. Right, so I want to view this as taking the derivative of the outside function. But then I'm going to go times by the derivative of the inside, which is the derivative of 2x cubed minus x, which is 6x squared minus 1. That's the derivative of the inside. So as you get good at this this type of thing, I mean, feel free to use whatever notation makes the most sense to you, and actually get fluent at using either. But once you get pretty good at it, you maybe don't need to introduce that intermediate variable u. You can just use the outside inside rule. However, as the next example we're going to look at demonstrates, it's very important that you can visually determine what the inside functions are, because you can write the composition of like 3 or 4 functions, and you want to make sure you understand which functions are in the inside and which one is the most inside, and be able to kind of unravel the chain rule effectively and accurately, and not miss any of the interior functions. So again, 2 ways of doing it. I would just say do whatever works at the beginning to lead you to the right answer. Why don't you go ahead and try this? Maybe pause the video and give it a try. So I'm going to assume you pause it, and then I'm going to write the answer down, and you can see how you did. Alright, so if that went well, you should have gotten that g prime of x, g prime of x equals negative 5 halves 6x cubed minus 4 to the negative 3 halves times 18x squared. Now if you simplified it, which you don't have to do, you might have got this. All right, so hopefully that went well. If not, maybe go and try to examine what went wrong.